In March of 2011, the Fukushima nuclear disaster began, following a powerful earthquake and subsequent tsunami striking northeastern Japan. These natural disasters caused the meltdown of 3 reactors and release of radioactive materials due to the failure of the reactor cooling systems. The disaster resulted in the evacuation of thousands of people along the coast and has had long-lasting effects on the environment, public health, public opinion, and the operation of nuclear reactors. It is considered one of the worst nuclear accidents in history, along with Chernobyl and 3 Mile Island. Join me, Sammy, along with Gabe and Chris as we explore what happened and how to continue on from the Fukushima disaster. In the 1950s, nuclear power was just an idea in Japan, not a hard, fast concept. The main source of electrical power in Fukushima and neighboring Tokyo was the Jobon coalfield just north of Tokyo. They produced 4.3 tons of coal in a year, ensuring Tokyo and all surrounding locations remain powered. Because of that, in 1961, discussion began between a local power company, Tokyo Electric Power Company, TEPCO for short, and the towns of Okuma and Futaba. 2 nuclear sites would be built, 11 kilometers apart from each other. Construction took place between 1971 and 1987. The result was 6 nuclear reactors at the Daiichi site, which directly translates to number 1 in Japanese, and 4 reactors at the Dai-ni, or number 2, site. The Daiichi plant consisted of 6 General Electric boiling water reactors, known as the Mark I containment, designed by General Electric, Toshiba, and Hitachi in the early 1960s. The Dai-ni plant operated 4 of the same style of reactor model. With each unit containing over 400 fuel assemblies, the Daiichi and the Dai-ni plants together were responsible for over 10,000 megawatts of electricity to the city of Tokyo. The shape of the reactor was a freestanding, bulb-shaped dry well with 30 millimeters of steel backed by concrete. A wet well constructed below was torus or donut-shaped with 3,000 cubic meters of water as an energy-absorbing agent should a reactor accident occur. This design protected against a loss of coolant accident of any size of piping in the plant. If a loss of coolant accident were to occur, steam from the dry well would travel through the vent lines of the primary containment and into the suppression chamber or donut to condense. Additional safety was provided with safety relief valves that would also vent directly into the pool. Unfortunately, no gas buildup would occur and not condense like water would. Because of this, a 120-meter emissions stack was also built to relieve pressure outside of the system. The concept of a reactor is to boil water to make steam. The primary cooling method for the reactor on screen would force steam from the reactor vessel to travel via the red line to the turbine, spin the turbine, and produce energy. From there, the steam would travel downwards to the condenser below, where it would condense back down to water with help from cooling water of a nearby river. The condensed water would be pumped via steam-driven pumps back to the reactor to complete the cycle. There were also 2 jet pumps to recirculate water around the shroud and core to maintain core temperature. If the plant were shut down, the method of cooling would shift. The steam would bypass the turbine via the turbine bypass line and be sent straight to the condenser to finish circulation back to the reactor. When the reactor was shut down and maintained at lower temperatures, a residual heat removal system with smaller pumps were used to circulate water. This is the light blue system near the bottom of the diagram. This system would circulate water from the pressure vessel to the residual heat removal heat exchangers by use of electrical pump. Surface water would be pumped through that heat exchanger, allowing a method of cooling before the water was sent back to the reactor vessel. This system was supported by emergency diesel generators. All other systems in the plant were not. Unlike many similar plants in the United States, the emergency diesel generators and switchgear for these reactors were located on the ground floor of the buildings rather than at an elevated height, leaving them susceptible to flooding and ground floor damage. At the time of construction, little research had been done about weather and tsunamis in the area along with their devastating effects. The height of the reactor site was the first big discussion and stopping point for the project. The design height was based on a 1960 Chile tsunami. That tsunami reached heights of 3.1 meters inland. So, to stay above that hypothetical height, the Daiichi plant was built at 10 meters above sea level and had seawater pumps built at 4 meters above. Another critical number to take into account for the construction of the Daiichi and Daini plants is something called run-up. Run-up is the highest inland point a tsunami wave could reach. Now, the Daiichi and Daini plants were built on the top of a hill in an attempt to keep them out of tsunami range. That hill, however, was sloped, allowing water to easily run up the side of it, another point that the engineers had not thought to fully develop and test at the time of construction. Gabe is up next to tell you just how devastating this event actually was on that tragic day in March of 2011.
Hello, my name is Gabe Wishon. I'm going to be going over the earthquake, tsunami, and the immediate impact of this disaster. At 1446 on March 11, 2011, the Great East Japan earthquake occurred 45 miles off the northern coast of Honshu Island, Japan. Also known as the Tohoku earthquake and tsunami, this undersea quake was the fourth strongest in recorded history, with a magnitude of 9.0, which lasted for over 2 minutes. As a newly qualified sailor reporting to the USS George Washington, fresh out of NNPTC, I had just arrived in Japan 2 weeks prior, leading to a day that I'll remember the rest of my life. Even as far south as Yokosuka Navy Base, the massive size of this event was abundantly clear. The impact and scope of devastation from the earthquake and tsunami was immense and affected Japan on many levels. In a report from the Director General published years after the event, it was noted more than 15,000 people had been recorded as died, along with 6,000 injured and another 2,500 people missing. The first tsunami waves reached Fukushima Daiichi nuclear power plant at about 40 minutes after the earthquake. This first wave was only about 4 to 5 meters and was successfully repelled by the tsunami seawalls that were designed for up to 5.5 meters. 10 minutes later was when the nuclear catastrophe really began. The second and largest wave hit with a run-up height of 15 meters, and it overwhelmed the seawalls and inundated the site. The nuclear incident further compounded the chaos and devastation the nation was experiencing. Evacuations from the Fukushima Daiichi plant added another zone of about 20 to 30 kilometers, with some people still not having returned to their homes all the way to this day. Immediately upon the earthquake's occurrence, the Fukushima plant went into an automatic shutdown for the 3 online reactors. At the time, the operating reactors were those of units 1, 2, and 3. The other reactor units at Fukushima Daiichi were already shut down for fueling and maintenance. The next issue faced by the plant was a dilemma of decay heat removal, which the equipment is dependent on electrical power. There was damage to on-site switchyard equipment, off-site substation equipment, and the power lines supplying off-site AC power to the plant. This led to a loss of all off-site electrical power. Emergency diesel generators, or EDGs, automatically kicked on to successfully restore on-site power. From the IAEA Director General report, it was noted, the wave flooded and damaged the unhoused seawater pumps and motors at the seawater intake locations on the shoreline. This meant that essential plant systems and components, including the water-cooled EDGs, could not be cooled to ensure their continuous operation. The wave flooded and damaged the dry cask storage building located near the seashore between units 1 through 4 and units 5 through 6. There were no significant impacts on the cask or the fuel stored in them, as was later confirmed. Water entered the flooded buildings, including all the reactor and turbine buildings, the common spent fuel storage building, and diesel generator building. It damaged the buildings and the electrical and mechanical equipment inside at ground level and on the lower floors. The damaged equipment included EDGs or their associated power connections, which resulted in the loss of emergency AC power. Only one of the air-cooled emergency diesel generators, that of Unit 6, was unaffected from the flooding. It remained in operation, continuing to supply emergency AC power to Unit 6, safety systems, and allowed cooling of the reactor. When this large wave hit site, the EDGs were flooded with 5 meters of water, and fuel tanks were swept away and left unavailable. The other EDGs that were dependent on seawater cooling were also lost, as the damage from the tsunami affected their seawater pumps and seawater intake locations. The emergency DC battery banks were also now damaged by the flooding. At this point, the site was dark with no electrical power. Due to the blackout, operators were no longer able to monitor some of the essential plant parameters like reactor pressure and reactor water level. Unfortunately, there were no procedures addressing the loss of all AC and DC power to direct the operators on immediate actions. Now in a blackout, pumps had failed, control valves were left inoperable, and operators had become blind with the failure of instrumentation. With the increasing levels of radiation, the initial indication was present that fuel rods had become exposed, which would lead to significant increase in temperature due to the loss of cooling. With all the cascading damages and loss of cooling, at 15:36 the next day, there was an explosion on the service floor of Reactor Unit 1 that injured workers of the response team. The explosion was determined to come from the buildup of hydrogen produced by zirconium oxidation. This explosion caused additional serious damage to the seawater injection systems and electrical power supply lines, as well as spread contaminated debris all over site. During the following few days, water level was lost and led to an additional hydrogen buildup in other units, causing further fires and explosions to occur. The loss of cooling and overheating of the reactors ultimately led to a partial meltdown and the official decommissioning of the sites, with significant explosions occurring in Units 1, 3, and 4. I would now like to return our presentation to Sammy for the next sections of our project.
Following the tragic accident that occurred March 11, 2011, researchers and engineers alike were forced to take a step back and truly evaluate all that went wrong. How had this tragedy occurred, something with such a magnitude that the engineers at the time had never imagined? The first design flaw laid in the physical location of the buildings and equipment. Looking at the interior of the building itself, as cross-viewed above, the emergency diesel generator room was placed on the ground floor with no backup power supplies on the premise. The dotted line indicates the height of the tsunami wave at its peak, 14 meters. The generator room was built at a height of 10 meters, above the critical point that the contractors had calculated, but more on that later. The crucial emergency equipment was placed directly in the path of destruction. Had they been placed at a higher point in the plant, much like similar United States plants, this catastrophe could have at least been minimized, as cooling would have been more reliable in the system. The same can be said for the seawater pumps, as they too were lost as soon as that initial wave impacted the plant. Because of where those seawater pumps were located, even if emergency power had been available, there were no cooling systems able to remove the generated and rapidly building heat. Not only was the building layout in jeopardy of natural disasters, the location of the building itself was placed in a precarious position. The Daiichi and Daini nuclear reactors were placed at the top of the hill, a sloping hill. When discussing tsunami damage and calculating heights, a factor called run-up should also be mentioned and analyzed. Run-up is the highest inland elevation the tip of a tsunami flood reaches. What this roughly means is that as a tsunami wave hits, the water does not simply stop at the hit point, but continues to travel inland, gaining momentum and speed as it collides and travels. This calculation was hardly taken into effect when the Daiichi plant was designed and constructed. The only number TEPCO focused on was the maximum design basis of a tsunami, clocking in at 3.1 meters above mean sea level. Because of that reason, the seawater intake was built at 4 meters above sea level, and the main building located on that slope 10 meters above sea level, well above what TEPCO viewed as the potential threat. With run-up factored in, the maximum height the tsunami reached was approximately 14 meters above sea level and some locations even reported a height of 17 meters, well above the 3.1 meters TEPCO was concerned with. The building was located in the perfect position to be struck by that tsunami wave, damaging an extensive amount of crucial equipment. Construction for these nuclear plants began in the early 1960s, when analog systems were in their prime. However, this casualty occurred well over 40 years later, past the emergence of digital and remote monitoring. Yet, those analog systems remained in place. This became another design flaw in the system, a lack of updating as new technology became available. This type of casualty was never even imagined, and due to this, cabling and batteries had to be scrounged for by operating personnel in an attempt to regain instrumentation in the plant. This alone delayed any response times, as the operators physically could not monitor the plant condition and take any necessary action until some method of remote monitoring was made. While the design of the Daiichi reactor had some fatal flaws, the construction itself was not the only thing to blame when it came to the Fukushima disaster. At multiple points along the construction and operation of the Fukushima nuclear power plants, TEPCO failed to either recognize potential problems or simply chose to ignore changes. A quick dive into previous nuclear reactor accidents would have shown the blameless flood of 1999. In 1999, two large storms sequentially swept over the Blaise nuclear power plant in France. These storms led to severe flooding in key areas of the plant, rendering emergency service water pumps virtually inoperable and prevented personnel from assessing the plant due to debris and floodwaters inhibiting movement. Had this accident been reviewed, perhaps the generator and seawater pumps could have been located in a different area, but unfortunately, this did not happen. Another human error in this accident was the lack of weather pattern tracking in the area. The International Atomic Energy Agency requires a history of 10,000 years to monitor seismic activity in the area prior to construction of any nuclear power plant. In the beginning stages of the Daiichi plant, TEPCO chose to only reference back to the 1960 tsunami off the coast of Chile as their design height basis. On a recently gathered list of tsunamis in the region over the last 10,000 years, 12 tsunamis had an amplitude over 10 meters, with 6 of those having an amplitude well over 20 meters, well above the design basis TEPCO chose of 3.1 meters. Finally, countless simulations were conducted when constructing the Daiichi and Daini nuclear reactors. Natural disasters such as earthquakes and tsunamis were tested, but unfortunately, these simulations were extremely conservative, assuming that complete core meltdown was impossible and that the meltdown would stop prior to burning through the pressure vessel, keeping all radioactive products relatively contained. They also tested with much smaller earthquakes than the one experienced that day in March, hitting at a magnitude they never thought possible. Next, Gabe will tell you how the emergency response and management was handled after the casualty.
In accordance with TEPCO's disaster response manual, there was an emergency response center at the Fukushima Daiichi nuclear power plant that was headed by the site superintendent, which was established around 15 minutes after the earthquake. A request was sent out for additional staff and equipment to support the incident, but extensive damage to transportation infrastructure initially hindered these efforts. TEPCO personnel were dispatched to the site to assist with tasks including restoring power, monitoring instrumentation, injecting cooling water into the reactors, removing rubble, and monitoring radiation levels. Workers at the site were expected to work very long hours and in very difficult conditions to perform the mitigatory actions. The Japanese government prime minister issued a declaration of nuclear emergency at 1903. This was more than 2 hours after being notified by the power plant team of the events at Units 1 and 2 that should have been classified as a nuclear emergency. The national government was involved in discussions for mitigation actions, such as injection of seawater for fuel cooling. The Japanese government was responsible for issuing evacuation and shelter-in-place zones, which changed several times but eventually reached 20 kilometers. Japan SDF, police force, and firefighters were also dispatched to the site to help with activities, including operating large equipment needed to pour or spray water onto the spent fuel pools in Units 1, 3, and 4. They provided helicopter surveillance of the spent fuel pools. The U.S. military provided assistance in the emergency response for the earthquake and tsunamis, as well as conducting aerial monitoring surveys by fixed-wing and helicopter flight operations. By the 25th of March, 500,000 gallons of fresh water had been provided by the U.S. Navy to support cooling efforts at the plant. The Japanese and international nuclear regulatory agencies, specifically the IAEA, played a major role in communications during the event. At the time of the accident, the IAEA had 4 roles in response to the nuclear or radiological emergency: notification and exchange of official information through officially designated contact points, provisions of timely, clear, and understandable information, provision and facilitation of international assistance on request, and the coordination of interagency response. The NEST team, Nuclear Emergency Support Team, was a team of expert engineers and scientists that operate under the U.S. DOE's National Nuclear Security Administration. The NEST team was deployed in response to this incident. NEST personnel were involved in the aerial monitoring, health physics, and atmospheric monitoring. This team played a critical role in forming the Japanese and U.S. governments to protect public health. Medical professionals also played a role in the response to the nuclear accident. There was necessary medical treatment and monitoring for the emergency workers. I'd like to go over some of the experiences that were seen by the first responders and survivors of this incident. The Tokyo Fire Division Chief Yasuo Sato dispatched 119 firefighters to the Daiichi disaster zone. Sato recalls, although the Tokyo Fire Department is responsible only for Tokyo and not for nuclear power plants, we thought we might get summoned for help, as we are the experts in firefighting and water pumping. At that point, we decided to start our research about how to handle this kind of a case. When the firefighters arrived at the scene of the reactor, they discovered the path from the sea to the plant was strewn with rubble. Rather than carry their hose by car or truck, they'd have to drag it by hand, more than 800 meters down to the sea. Asafumi Yoshizawa was a nuclear engineer on shift at the Fukushima Daiichi plant during this event. He said in an interview, "I managed to look out of a window, and I saw parked cars bouncing up and down from the sheer force of the earthquake. I had never experienced anything like it. We knew that we would not be replaced on site. No one was forced to stay, but those of us who remained knew that we would be there until the end. We knew that we were the only people capable of saving the plant. Our determination surpassed all other considerations." He also said, "Generally speaking, people in Japan believe we were the cause of the accident. It's important to bear that in mind. As TEPCO employees, we have to take responsibility for the accident and to ensure that it never happens again. It's a matter of regaining people's trust, but it will take time." 7,500 family members of the U.S. military personnel who were living in Japan were sent back to the States. My ship, the USS George Washington, was kept on standby in the Sea of Japan. We pulled out on only one reactor just over a week after the tsunami, with shipyard on board coming from NSPS to go alongside us and complete the SRA period. During this time after the incident, flight deck personnel were assigned to the decontamination efforts on the flight deck. While myself and others in reactor department, we were tasked with measuring the fallout and stationed at decontamination centers to frisk and clear personnel coming off from the upper decks. Other auxiliary impact of the situation was our HVAC and ventilation systems. They now all measured fallout. The shipboard APDs started going off the very next day after the incident. One of the countermeasures we attempted was to put socks on all the vents in the plant. Frisking out these vents confirmed contamination was coming in through the ventilation systems. There were also 145 members of the special unit called Chemical Biological Incident Response Force, and they were dispatched to Japan, but their activities were limited to the outside the 80-kilometer radius from the Fukushima nuclear power plant. The remediation efforts are focused on the goal of reestablishing an acceptable basis for a fully functioning society in the affected areas. The strategy specifies that priority areas for remediation are residential areas, including buildings and gardens, farmland, roads and infrastructure, with an emphasis on the reduction of external exposures. External dose from radionuclides deposited on the ground and other surfaces is the main pathway of exposure. Internal doses continue to be controlled by restrictions on food as well as through remediation activities on agriculture land. The first steps in developing a remediation program are the definition of appropriate reference levels and the establishment of a remediation strategy to achieve the required reduction in radiation exposure to members of the public. It is important in setting reference levels within a range that are not too high, which would jeopardize the required safety objective, or too low, which could result in a less than optimal use of limited resources. A major method being used for decontamination has been high-pressure washing and topsoil removal. Within 5 years, the majority of the decontamination efforts in the special decontamination area had been completed. Investigators performed in residential areas of Tamura and Naraha municipalities showed that the ambient gamma dose rates had been reduced by an average of 36 to 46%. Following the emergency phase, TEPCO and the relevant government agencies established a strategic plan, the mid and long-term roadmap towards decommissioning the Fukushima Daiichi nuclear power station units 1 through 4 for stabilization and decommissioning activities. It is a comprehensive, high-level strategic plan for those supervising the recovery. Decommissioning is projected to be completed on a timescale of 30 to 40 years, according to the Japanese authorities' estimates. Water enters damaged reactor buildings, becomes contaminated, and poses a particularly challenging problem due to the large volumes involved. Water continues to enter the reactor buildings at the Fukushima plant in two ways. Water is injected into the reactor cores for cooling purposes, and there's the ingress of groundwater. There are currently groundwater bypass pumps in place to reduce the amount of contaminated water that would come from the uphill groundwater source. The removal of spent fuel rods has proven to be a very challenging task in recovery. By 2019, TEPCO had successfully managed to remove the spent fuel rods from Unit 4, but Units 1 through 3 will pose a much greater challenge, as they were the ones that melted down and have a higher level of radiation and physical damage. It is currently not possible to protect the end state of the Fukushima Daiichi nuclear power plant. None of the 3 plants elsewhere in the world that experienced the most severe fuel damage in previous accidents has yet achieved the final end state for complete decommissioning. I would now like to turn our presentation over to Chris for the final sections of our project.
Good evening, and thank you for the introduction, Gabe. I'll be discussing with you the lessons learned immediately following the Fukushima Daiichi nuclear incident and the reevaluation of safety standards and regulations, the part it played to further the naval nuclear power and the impact it had on how we are today. So first, immediately after, there was a team put together of highly trained and experts that would go inspect the Fukushima and other sites to ensure that they were up to standards. Same thing we like to do on now in the Navy. We have a mobile training team, ensuring that we are up to standards in terms of training, all our knowledge, casualty response. The same thing they did back then to ensure that they doesn't happen again. Another thing that did, one of the regulations that occurred after was ensuring that they had defense in depth. And so what that did was that if one thing failed, the whole system would not fail. So multiple contingencies were put in place after, which I will talk about in a couple more slides from that, about how the multiple things that occurred that caused the Fukushima Daiichi event that no longer would happen. And additionally, they had the emergency action plan was created. The emergency action plan is sort of like a reactor accident drill in the Navy that we do. It's a yearly requirement now where if something does occur, then we can contain it, treat the wounded or ensure the public is informed, everything to ensure that the site and accident is contained. The emergency action plan is also called a countermeasure. And it's going to be identified and a plan for implementing such measures is developed in an attempt to minimize the risk arising from exposure to ionizing radiation and risk associated with public anxiety. Because the public view of nuclear power is very important, and how we contain it really affects how much further we're going to be able to operate and expand nuclear power. So immediately following the incident, the NRC required stationing blackout mitigation strategies. So that's going to be dealing with a sustained loss of power, which is one of the major things that happened in this that caused the incident. So that's one of the actions that civilian plants and Navy nuclear power trains to, is having sustained loss of power and having that backup power in case it happens. Another is on-site emergency response capabilities, and making sure that you can get to it in case the accident does occur. Filtering and confinement strategies, so being able to contain it. We take strategies the same way in the Navy, containing the accident in case one would occur, get trained on that, ensuring that our level of knowledge remains high on what containment is, and then setting it that way. Like I said, in case one would occur, we could keep moving forward and protect from getting the environment. Containment venting system. This applies to boiling water reactors with certain design marks 1 and 2. So the main concern here is pressure control and removing the heat, so you can prevent core damage, because core damage is ultimately how your fission products is going to get to outside the ship or outside the plant. So that'd be the major thing, is making sure that requiring work when all power is lost, you can actually still have a containment venting system to make sure that would occur. To be another re-evaluation that happened after the Fukushima Daiichi event. It's like any major accident, the Fukushima Daiichi incident was heard all around the world, so the French Nuclear Safety Authority described implementation of both fixed and mobile equipment that could potentially prevent a large release, including high resistance diesel generators and pumps, able to function in extreme scenarios such as major earthquakes or flooding. That was just an important feature, because you have to think about everything when it comes to designing or plants, especially nuclear power. Set off that chain reaction, obviously bad things can occur. Then the availability of alternative sources of water for cooling was also prescribed under the same conditions. And the flyaway team was established that could be on site within 2 to 4 hours. So having that on the ready, making sure those people are identified, was super important. Still super important today. It's something we do. Just in case something were ever to happen, we'll be ready. So the NRC also, after the Fukushima Daiichi event, asked each plant that has a license to do the following: inspect or walk down currently installed earthquake or flooding protection features and correct degraded conditions. That's why it's important that the inspections happen pretty frequently. They can inspect and make repairs as necessary. Sometimes if they have to do maintenance shutdowns or availabilities, then they can do that. But as long as those standards are withheld, this is one of the things that wouldn't happen, so they can avoid the earthquakes and floodings. Now the design teams that design plants and nuclear power plants have a lot of computer simulations to run those simulations that's happened in the past and do testing at centers to make sure that they can withhold that. Enhance the emergency plans to ensure sufficient staffing and communication capabilities multiple reactors at a single site are affected by the events. Just making sure you get that training that it's on that site, make sure that occurs is very important. So as you can see in this slide, that it will take multiple things to occur to get an accident such as the Fukushima Daiichi event or any other to occur after this redesign. You have your portable backup pumps, hoses, and diesel generators in case you lost power on site. Installed backup batteries and pumps. You have if you have your loss of on-site power, you have those other features to take care of that occurs. Your regional response and supplies from off-site and regional response centers. So those are the mitigating strategies overview of basically how the plants were redesigned after. So that way, in case it ever happens again, it just will take so many factors to do the same thing. So now moving into talking about the Fukushima Daiichi and then comparing it to the other incidents that occurred over the past. Something we always look back on and study in naval nuclear power. That way we don't make the same mistakes and learn from them. So first, the Fukushima Daiichi. It's the highest INS rate in rank 7. So basically the summary, Great East Japan earthquake, 9.0 on the Richter scale, off the Sanriku coast of Japan. Generated a series of tsunamis along the coast of Japan. The wave's average height is 15 meters. The design basis tsunami was 5.7 meters. So as you can see, it was much, much greater than the design basis. Consecutive nuclear meltdowns and reactors explosion. The causes, emergency cooling system generators located in the basement. Safety records, falsification. TEPCO ignored flood warning, geographic location. Consequences to erratic spread of radioactive plumes. Contaminated soil and seawater, harmed cattle and livestock industry. Neighborhoods uninhabitable. Government mistrust and instability in nuclear industry. Now we're talking about Chernobyl. In comparison with Chernobyl, it's also an INS rank 7, so the highest. It was USSR April 25, 1986. Causes faulty design of the RBMK reactor, safety violation, less experienced and poorly trained operators error. And so the consequence of that is 7 times 10 to the 6 curies of reactivity release, huge heat transients release, 31 on-site operators killed, death of 7,000 to 10,000 liquidators, thyroid cancer in children, general health of the inhabitants. So major effects basically due to those causes that could have been prevented. So that's the comparison with Chernobyl. So this is the comparison with 3 Mile Island. It was an INS rank 5. So if you don't remember 3 Mile Island, you should definitely look that up because we live in America. And it was the worst nuclear accident in the United States and commercial nuclear industry. Completely destroyed the reactor due to a loss of coolant accident. So the causes of that was mechanical failure of the valve in the secondary loop, equipment failure, faulty design of the pressure operating relief valve indicator, violation of NRC safety regulations, inaccurate water level measuring instrument inside reactor core. Consequence of that, post-traumatic stress and public psychological impact on pregnant women and mothers, mismanagement in hospitals, and adverse impact on nuclear industry. So all these things could have been avoided, as like I talked about the reevaluation of safety standards, and have an inspection team constantly come out, inspect the equipment, make sure it's getting fixed, making sure you just are abiding to safety regulations. SL1 is just another one I wanted to talk about. It's only an INS rank 4, so it wasn't like the 7s we were talking about Fukushima. So it happened during a routine maintenance. Central control was moved too far, causing the reactor to suffer prompt criticality. Steam explosion release reactivity was contained within the building, thankfully. So it causes improper removal of the central control rod, uplifting of the rods by 50 centimeters instead of 10 centimeters. So you can see there's a lot of room for error there, and the stickiness of central rod. Consequences of all three operators on site died. Huge power surge led to fuel colliding, swelling. The reactor vessel, 5 metric ton weight, disengaged and jumped to a height of 3 meters. I wanted to include this major causes. So major causes, you can look back on any of the nuclear incidents that happened. So they all had a lot of commonalities. So faulty design, equipment failure, inadequate safety and warning system, violation of safety regulations, lack of trained professionals, operators error. So you can just see that how every one of those in history could have prevented if we just take a little more time. People have been trained, follow the safety regulations, but now we have become more strict, have those inspection teams found out. The operators go through a lot of training, and like in the Navy nuclear power program, we personally go through 18 months of training, and then we keep getting constantly trained in the fleet. So that is a Department of Energy requirement. Being able to, for example, being able to pass a quarterly CTE, and then knowing the designs of your plant, how to fight casualties, and then making sure that you're following safety regulations. I wanted to talk to you about the nuclear world model here in this particular slide. This is something that we train in Navy nuclear power. How we have the maintenance person and their comfortability and training level. Then you have the technical work document, the procedures, knowing the operating procedures, and the supervision. So any one of those bubbles could be small, and you would have to compensate by increasing the other two. You might not have a great familiarity with the procedures or how to operate, so you just increase training, increase supervision, making sure your maintenance person is ready to go, making sure the increasing supervision, making sure that way we keep safe, reliable operations of the plant and don't have any nuclear accidents. So the world is becoming more and more digital, and demand for electricity is ever increasing, and so our goal is to find more cleaner energy, and the way to do that is having nuclear power, so that way if we're looking and learning from our previous incidents and moving forward and retrieving that trust, we'll be able to expand the nuclear power industry. It's important that we learn from each commercial plant and each platform. So the Navy, for example, each platform that they have created has been ever evolving and getting better and better with technology that's been occurring. We have been more efficient with our waste. There's becoming new technologies now that is using reactors that will run on the waste that's occurred from previous reactors. So that's a cool new feature. And finding new ways, more reactor power, such as small modular reactors, they're becoming more and more popularity. And so the IEA's projections for global installed nuclear power capacity is indicates an increase from 2016 levels by 42% in 2030, by 83% in 2040, and by 123% in 2060. The low case projects a decline in capacity by 12% in 2030 and 15% in 2040 before rebounding to present levels by 2050. So that's why it's important that we have the trust of the public. That way we can match that need and just keep increasing. Okay, so the conclusions of this, I hope that you guys have learned about the summary of the Fukushima event, the design of the Fukushima plant, some of the first-hand encounters that Gabe has presented, then the reevaluation of safety standards and regulations that were put in place right immediately after the event, and then the comparisons that I've told you about the different nuclear accidents in Fukushima. I want to thank my classmates, Gabe and Sammy, for their hard work and teamwork during this course. And then acknowledge Mr. Massey for his feedback and helping in this presentation and our work for this policy together. But our strive for cleaner energy is built on nuclear power, so we're going to be moving towards that. So keeping the trust of the public. And so every great generation and invention starts with great thinkers. I hope you guys have enjoyed it. Thank you for listening to this presentation.